Okay, in chapter 4, we finally make it to the trigonometry part of the course, but before we get to the actual trigonometry, we need to talk about some geometry to get us ready for the trigonometry. First of all, realize what is trigonometry. You know, when you see the metry at the end, it's study of, but what does the tri refer to? Trigonometry. Tri is 3. All trigonometry is the study of triangles. So please don't make it more difficult than it is. We're just studying triangles here. All right, so first we have a definition at the beginning of section 4.1. It says an angle is formed by rotating a ray around its endpoint. Okay, so I've left room there. I always underline the words I'm defining. So I'm defining angle here. So first, what's a ray? A ray is a portion of a line. It's a part of a line that starts at one point and continues through another. So if I call this point A and I put point B here, a ray would start at A and continue through B. I'm drawing it this way horizontally because that's often how we're going to draw angles, and we'll do that in a minute. Okay, so we have this ray, and so this is the end point. We call this the vertex. And where have you seen that before? The vertex, remember we had the vertex of a parabola. So we have the vertex here of an angle. This is called the initial side. And then we're going to rotate that angle about its vertex. I'm just going to draw something. So suppose I rotate it that much. And then this is called the terminal side. Okay. So when I first learned about angles and triangles, say, I always thought of the angle as the space right here. But that's not really what an angle is. Right? An angle is an initial side, a rotation, and a terminal side around a vertex. So like when you used to play like the game of life and you had a spinner, right? Think of it, that's where the spinner started, that's where the spinner ended. So initial side, terminal side, the vertex, and the rotation. And of course the arrows mean this goes on forever. The angle goes on forever. Okay, so that's the actual definition of an angle. So there's initial side, a terminal side, and a rotation involved. The next definition says if the rotation of the terminal side is counterclockwise, the angle is positive. If the rotation is clockwise, the angle is negative. So in this picture I've drawn here, what sort of angle do we have? Is it a positive angle or is it a negative angle? Well, it's going counterclockwise, so that's a positive angle. Okay. Next, notice here, I just have this floating around. I mean, you can have an angle just floating around with no sort of context. But this next definition is putting these in context. Let's just focus on the first sentence here. An angle is in standard position if its vertex is at the origin and its initial side is along the positive x-axis. As soon as you hear origin and positive x-axis, that makes you think of the Cartesian plane, the usual xy, right, plane. So we have x and we have y, okay? So what does the definition for standard position say? Its initial side has its vertex at the origin and the initial side is along the positive x-axis. That's why I drew this one this way, because we almost always put these, when we put them in the xy plane with the axes, we almost always draw it that way. Now keep in mind, the book may not always say in standard position, but if you're drawing it with xy axes, always assume the angle's in standard position unless they say otherwise, which I can't even think of one example where the book actually does that. Okay? So if the initial side is here, you're in standard position. Notice the definition says nothing about where the terminal side is. So as long as your initial side is here, you've got standard position. It doesn't matter where the terminal side is. Okay? So for example, if I drew an angle like this would be standard position. And it has nothing to do with the terminal side and nothing to do with the rotation. That makes standard position right there. Okay, now the second sentence is another definition. Angles in standard position, initial side on the positive x-axis, having the terminal side on one of the axes, those are called quadrantal angles. Okay, so again, standard position, so the initial side is here. So to be a quadrantal angle, the terminal side has to be on one of the axes, positive x, positive y, negative y. So for example, if I put the terminal side here with that rotation, say, this is a quadrantal angle. Standard position because the initial side is here, terminal side is on one of the axes. Notice to be in standard or position or quadrantal, the rotation doesn't matter. Okay, so there's a quadrantal. What's another example of a quadrantal angle? Initial side here, because standard position. I don't know, put the terminal side here and rotate 1.5 times around. This would be a quadrantal angle. Standard position, initial side here, terminal side is on one of the axes. Okay, so quadrantal, the terminal side's here, 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 or here. Notice this is not a quadrantal because the terminal side's in the middle of the second quadrant. Okay, and then lastly, the definitions here. A degree is a unit of measure for angles. You already know this. One complete rotation is 360 degrees. Okay, so initial side is here. One complete rotation is 360 degrees. Notice in this picture, the initial side and the terminal side are on top of each other. Notice 360 degrees is a quadrantal angle because the terminal side stops on the positive x-axis. Notice what's interesting about the definition. I always give the example, if you were teaching first grade and you were trying to explain to the students how large 1 foot is, what would you do? Would you say, well, 1 foot's 12 inches? Or 1 foot's a third of a yard? The first graders would be, what? What are you talking about? How would you indicate that? You would show them a ruler and say, this is 1 foot, right? They could visually see 1 foot. Oh, that's how big 1 foot is. So 2 feet would be about like this and 3 feet would be about like this. Notice how they've defined a degree here. They didn't tell you what 1 degree is. They told you what 360 are. Now, why did they do that? Why didn't they just say, here's what 1 is, like you would with a ruler? Well, if I try to draw 1 degree, I have to chop this up into 360 pieces. As small as I try to make that to look like 1 degree, it's too big. Anything I draw is too big. So it's hard to show 1 degree. That's why they said 360. They figure you're mathematically mature enough to interpolate and figure out how big 1 might be if you knew 360. Okay, so just for practice here, we want to practice sketching some angles. We already did 360, but they say to do others here. So they say sketch the following angles in standard position. So always initial side on the positive x-axis, okay? Okay, so there's 4 of them here. So the initial side is always going to be on the positive x-axis. Okay. So the first one they want is 90 degrees. Well, how do you want to think of 90 degrees? Well, all the way around is 360. 90 is a fourth of that. So it's, and you already know 90 degrees is a right angle. So 90 degrees is the right angle. So the terminal side is here. There's a sketch of 90 degrees in standard position. Initial side here, standard position. Terminal side here with that rotation. Notice 90 is positive, so you move counterclockwise. Whenever your angle's in standard position, positive angles are going to be up and negative angles are going to be down. Okay? The next one says negative 180 degrees. Negative 180 degrees. So a negative angle is going to come down, right? It's going to go clockwise. Now where's negative 180? Well, all the way around is 360. 180 is half of that. So 180 degrees is halfway around in the negative direction. So there's negative 180. Notice both of these angles are quadrantal angles because the terminal side's on an axis, the terminal side's on an axis. The next one is 160 degrees. 160 degrees. Don't forget your degree signs. Always write your degree signs. Now, where's 160? Well, we did negative 180. There's a positive angle, so we're going up. Halfway around is 180, so 160 is a little bit less than that. And I'm not trying to be super precise, but try to be reasonable. So 160 is going to be almost to 180. So there's 160. Notice this is not a quadrantal angle because the terminal side is not on one of the axes. And then the last example here is negative 280 degrees. All right, so a negative angle, we're going to be coming down, right? We're going clockwise. Now, where's negative 280? Well, this was 90, negative 90. This is negative 180. 3 90s, right? 1, 2, 3 would be here. That's negative 270. So you have to go an extra 10 degrees. So there's negative 270 plus a little bit more. There's my negative 280. Notice this is also not a quadrantal angle because the terminal side is not on an axis. And that I've overestimated. That's way more than 10 degrees. Okay? But typically in trig, we're really interested in whether the angles are quadrantal or not. And if it's not a quadrantal, just which terminal, the terminal side of the angle is in which quadrant. I will often say, where does this angle live? And what I really mean is, where is the terminal side? So if I say this angle lives in the first quadrant, I'm really saying the terminal side of the angle is in the first quadrant. Okay, now just like other units of measure, right? Say, I mean, how many different ways do we have of doing length? Feet, inches, yards, meters, kilometers, miles, light years. I mean, there are a lot of different measurements for length. Why do we have so many measurements for length? Why don't we just do feet? Let's just do everything in feet. Well, I mean, that's fine if you're measuring a room or something, or, you know, the width of this whiteboard. But what if all the highway signs were done in feet? So you're out on the highway and it says Baton Rouge, 500,000 something feet. That's not, you're not going to be able to wrap your head around, large numbers like that. So it makes sense to have different units of measurement depending on what the use is. Likewise, you wouldn't want to measure everything in miles, because then if you were measuring the width of this whiteboard, it'd be 0.000, something miles, and then the numbers are way too small. Okay, so we have other units of measures for angles. So I can't draw this, but I had the picture, tried to draw a picture of 1 degree a second ago, which was way too small. Imagine chopping that tiny degree up into 60 pieces. We call each of those a minute, and the notation is prime. So you read that as 1 minute, okay? So prime means minute. Then each of those minutes you can chop up into 60 pieces that we call seconds. And we denote that with the double prime. Now notice you have to take this in context. If I just saw this and didn't know anything about trigonometry, I would assume this is 1 feet, 1 inch. Remember, we use the prime for feet and the double prime for inches. So you have to take it out of context, okay? So when you see it in this course, when they're talking about an angle, this is 1 minute, 1 second. Okay? So 60 seconds is a minute, 60 minutes is a degree. Okay? Right. Okay, so we want to do some computations with it. Before we do that, just to relate it to something I know you already know, suppose you watched a television program for 45 minutes. I'm talking about time units. And then you watched another program for 20 minutes. What's the total time you watched television? Right? So I said 45 minutes and 20 minutes. Well, you could say that's 65 minutes, or what? 65 minutes is an hour and 5 minutes. Once you get to 60 minutes, you converted that to an hour, and then you still have the extra 5 minutes. So the calculations here work the same. Once you get to 60 seconds, you get an extra minute. Once you get to 60 minutes, you have an extra degree. Okay? So the idea works exactly the same. So the next example says, add the following: 52 degrees, 41 minutes, 23 seconds, plus 17 degrees, 25 minutes, 40 seconds. So just like you did in grade school when you're adding decimals, we're going to start from the right, go right to left. So I'm just going to add down, but I'm going to carry, right? Once I hit 60, I'm going to carry. So let's add the minutes, seconds. 23 seconds and 40 seconds is 63 seconds. But what's 63 seconds? I've gone over 60, so that's 1 minute I'm going to carry and 3 seconds. Right? So 63 seconds is 1 minute. I carried the 1 minute and 3 extra seconds. Okay, now let's add the minutes down. I have 1 that I carried, 41 and 25, so that's what, 42, that's 67 minutes. Okay, so 67 minutes, well, I have 7 extra minutes, and the 60 minutes becomes 1 degree. And then you just add down, and that's 70 degrees. Put your units, right? When you mean seconds, put seconds. When you mean minutes, put minutes. When you mean degrees, put degrees. Okay, so again, that's 63 seconds. So that's 1 minute and 3 seconds. I carried the 1 minute. Add those down, you get 67 minutes. 67 minutes is 1 degree, 7 minutes. So I carried the 1 degree, and then you add down. Very easy. You just have to carry it. Now, likewise, we can do a subtraction problem. So the subtraction problem says subtract 22 degrees, 48 minutes from 40 degrees 10 minutes. Okay? Now here, what's the problem? I want to subtract 48 minutes from 10 minutes. There aren't enough minutes to subtract from. So remember when you were in grade school and you were subtracting two-digit numbers from two-digit numbers, if you didn't have enough of the two-digit here to subtract this from it, what'd you do? You had to borrow. Okay? Now if this were 50 minutes, you could just subtract down and be done. Very easy. Okay, so what do? I don't have enough minutes here to subtract 48 from, so I need to borrow a degree here. So I'm going to borrow a degree, so that makes it 39 degrees. So I've stolen a degree. When I bring the degree over here, it's 1 degree in 10 minutes. I still have the 10 minutes from before. 1 degree in 10 minutes is 70 minutes. Okay? So I borrowed a degree, making that 39 degrees. The degree comes over here as 60 minutes. But remember, I still have the 10 minutes here, so that's 70 minutes. Now you just subtract down, and you get 17 degrees. What, 22 minutes? Easy. Don't make these harder than they are. It's just when you hit 60, if you're adding and you hit 60, you carry. If you're subtracting and you don't have enough, you have to borrow. Okay, so that's that. Okay, now likewise, just like when the example I gave about watching a TV program for 45 minutes and 20 minutes, and we said 65 minutes or an hour and 5. Right, you can do it either way, but sometimes you want to stick to the same unit. So, for example, 45 minutes and 20 minutes is 65 minutes. Sometimes you don't want to mix units like the hours and minutes. So, so as an example to illustrate, suppose I gave you 45 degrees, 30 minutes. Okay, so this is mixed units, degrees and minutes, which is perfectly fine. But so notice the instructions say convert to decimal degrees. So they only want degrees here, and so instead of saying 30 minutes, you want this as a decimal. So the final answer is 45 point something degrees. So the question is, what fraction, what decimal is 30 minutes of a degree? So this is one, there's no work to do. I just wanted to introduce you to the idea of the instructions. You know, convert to decimal degrees, okay? They mean get rid of the minutes. Well, how many minutes are in a degree? There's 60 minutes in a degree. 30 minutes is half of that. So this is half a degree. And how do you write 1/2 as a decimal? So this is 45.5 degrees. Don't write 0.3 because it's a 3 here, right? This is 30 out of 60, which is a half. And a half is 0.5 as a decimal. So the answer there is 45.5. Okay? So that's one you can eyeball, just using some basic arithmetic. But now we want to do ones that are a little more complicated. The next one says, let's look at 17 degrees, 21 minutes, 37 seconds. And they say convert to decimal degrees. So this has minutes and seconds. Now I'm going to work this out in a long belabored way, because I want to explain unit conversion to you, because you can use that in any sort of problem, not just one like this. And then once we work through it, then I'll just tell you how I will do this when I do my lectures, okay? I'm not going to work this out this long way every single time one of these shows up. But I want to teach you unit conversion that you can use in other situations. If you've done stoichiometry or the dimensional analysis in chemistry, you've done this before. Right? But if not, that's fine. I'm about to show it to you. Okay? Now, before I do a problem like this, I get an idea what I think the answer is going to be. Okay? For example, this is about 20 minutes. It's a little more than 20 minutes, but it's about 20 minutes. Notice 20 minutes is a third of a degree, because there's 60 degrees in a minute, and we're using 20 of them, right? 20 out of 60 is a third. So I expect this answer to be a little more than 0.33. It's less than 30 minutes, so it's not going to be 0.5. So it's somewhere between 0.33 decimal part would be between 0.33 and 5.5. Okay, so try to do that before you do a problem, and then you get a weird answer. You may have just hit a wrong button on the calculator. Okay, so here's what we're going to do. First, I'm going to convert the seconds to minutes as a decimal minute, like we did decimal degrees. Okay, so I'm going to take the 37 seconds and write it over 1 just so it looks like a fraction. Right? Now I want to multiply by a fraction here, so I'm changing units. Now don't try to put the numbers in. Students are in such a hurry to put in the numbers, they put them in the wrong place. I always try to put in the units first. If the seconds units are in the numerator here and I want to get rid of them, I want them to cancel out, where should they go over here? They should go in the denominator, right? Because then you have seconds over seconds, those units cancel. which means I want minutes to be up here because I'm trying to convert those to minutes. Right? So argue units first. Where do the units go? So seconds are going to be in the bottom, minutes are in the top. Now ask yourself, how many minutes or how many seconds? I want this fraction to equal 1. Now the numbers aren't going to cancel because they're different units. But I know that 1 minute is 60 seconds. So as soon as you put the units in, you can figure out where the numbers go. When I travel overseas and I have to do money conversion, I can't remember, am I multiplying by 1 point something? Am I dividing by 1 point something? I don't have to memorize that. I think of this, if I have dollars here, I need dollars here, and I need, say, euros here. And then how many euros is how many dollars? So I put the units first, then put the numbers in to make it equal to 1. Okay, so this is just 37 divided by 60. And I'm going to write, always use more decimals in intermediate calculations. If the problem says round your answer to 2 decimal places, don't do 2 decimals in the middle. You're rounding on the rounding and you'll be way off. So I'm going to write 0.61667 minutes. So the 37 seconds became 0.61667 minutes. Okay, so this became this. Well, how many total minutes do I have? I have the 21 minutes in the problem, plus the minutes I got from those seconds. So now I have 21.61667 minutes. I'm thinking that is over 1, just like I did before. So now I want to convert this to degrees. Okay? So I have the minutes units here. I want to get rid of them. I want them to cancel, so I'll put the minutes in the denominator, and I want to go to degrees. Right? So those units cancel. I will then have degrees, which is what I want. Now, how many degrees is how many minutes? So 1 degree is 60 minutes. So if I take the 21.61667 and divide by 60, I will then have degrees. Okay? So 21.61667. You should always punch in with me. If you need to pause the video to punch in, that's fine. But you should always punch in with me. Divide by 60. Okay, so I get, if I round to 4 places, I get 3603. Now that doesn't answer the question, okay? So the 37 seconds became this many minutes. The 21.61667 minutes became this many degrees. The problem said convert 17 degrees, 21 minutes, 37 seconds to decimal degrees. Don't forget your 17. Don't just stop here. The final answer is 17.3603 degrees. There's your final answer. Okay, so this is how you do the unit conversion in general. You can use this in any unit conversion situation like money or lengths, feet, inches, miles. You just have to know how many of one is how many of another. Okay, now this is not what I'm going to do when I'm lecturing and a problem like this comes up, okay? So if I need to convert this to decimal degrees, here's what I do. I don't work all this out. If you need to work it out, you can, but you have to be quick about it because that's typically the very first step. Think about what we did here with the seconds. I had the seconds here, the 37, I divided by 60, and I got the 0.61667. But then, I know I added something to it, but that 0.61667 got divided by 60 again. So I divided the 37 seconds by 60 twice. Now what about the 21 minutes? That was not involved here, but there's the 21. The 21 got divided by 60 once, okay? So the way I will always do this just quickly on the calculator so I don't have to do all this. Again, I want to teach you this so you can understand unit conversion because we're going to use it later and I won't have to re-explain. So on the calculator, I would type this in as 17 plus 21 over 60 because we divided this 21 by 60 once, plus 37 over 37, okay, we divided the 37 by 60 twice. Dividing by 60 twice is the same as dividing by 60 times 60, which is 3,600. So notice if you punch that in the calculator, 17 plus 21 divided by 60 plus 37 divided by 3,600, lo and behold, you get 17.3603. Okay, so this is how I'm going to do it now. Okay, so I would this is what I punch in the calculator, and there's my answer. Don't forget your degree sign. Okay, so when I do the lectures, when I get something like this and I have to do the conversion, I'm just going to type it in the calculator like that. Okay, so you don't have to work all this out, but I wanted to teach the procedure to you. Okay, so let's go the other way. Okay, the next one says to convert a decimal degree to degrees, minutes, and seconds. Okay, so it's 121.491 degrees. And they want the answer in degrees, minutes, seconds. Well, you know the answer is going to be 121 degrees. Okay, so that's already taken care of. So now let's look at the 0.491 degrees. And notice in the previous problem, remember I said that answer was going to be bigger than 0.33 and less than 0.5, and it was 0.36. So the answer made sense. Always see if your answer makes sense. Okay, so at 0.491 degrees, I want to convert that to minutes. Notice in the previous problem, we went seconds to minutes to degrees, and now we're going to go degrees to minutes to seconds, the other way around. Okay, so I want to get rid of degrees, so degrees go in the bottom, minutes go in the numerator, and then how many degrees is how many minutes? 1 degree is 60 minutes. So if I multiply the 0.491, punch along with me, times the 60, I get 29.46 minutes, right? The degrees cancel, I went to minutes. So notice my answer so far is 121 degrees, 29 minutes. So notice I pulled the decimal part here to convert to minutes, and now I'm going to take the decimal part here and convert to seconds. So now I have 0.46 minutes over 1, and I want to convert that to seconds. So I want to get rid of the minutes, so those go in the denominator, and I want seconds in the numerator. And how many seconds is how many minutes? 60 seconds is 1 minute. So then 0.46 times 60 is 27.6 seconds. Now if I had another unit besides minutes and seconds and something else, I'd pull up the 0.6 and go again. But we're done. I'll just say 27.6 seconds. Right? So this is going from decimal degrees to degrees, minutes, seconds. And this answer makes sense, doesn't it? 0.491 degrees is a little bit less than half a degree. Half a degree is 30 minutes, and we're a little bit less than that. So that the answer makes sense. It's always nice to check your answer a completely different way. We know how to convert from degrees, minutes, seconds to decimal degrees, and decimal degrees to degrees, minutes, seconds. So we just did a problem going from this form to this form. So if you do 121 plus 29 over 60, plus 27.6 over 3,600, you should get that. Now, you may be off a little bit because we rounded, but it should be very, very close, and then you think, okay, I did it right. So it's nice if you do this to get this, do it, the way we just did it, and see if you get the same answer. Notice in the previous problem, we divided by 60, then we divided by 60 again. Notice here, you multiplied 60 and then multiplied by 60 again. Okay? Okay. Now in this section, it's a long section because there's a lot of little topics. So now we're going to shift gears again. Wait, let me make sure I'm in the right place. Okay, right. Okay, so the next example says an angle that has its vertex at the center of a circle is called a central angle. So notice the first definition of angle just had it floating out in the middle of the plane. And then we put it with the XY axes, right? We put it in relation to that, and the vertex was at the origin. That was standard position. Now we're putting an angle in relation to a circle. So here's a circle. It's supposed to be a circle. And an angle has its vertex at the center. So there's the vertex. So the initial side and terminal side just go wherever. So there's the initial side, there's a terminal side with some kind of rotation. Often when you do a central angle, you don't put the rotation in, but we will in these application problems. So this is a central angle. So typically we'll use, say, theta, the Greek letter theta. Please don't misinterpret that as a 0. Again, look in the book and you can see that the type that it looks like that. That's the theta. Okay, don't think of it. It's standard procedure to use Greek letters for angles in trigonometry. Okay, so there's a central angle. Okay, now don't draw this yet because I'm going to erase. Okay. Notice this central angle here intercepts an arc. Arc is spelled ARC, not like Noah's Ark, ARK. So there's an arc of the circle, ARC. Notice when you have a central angle, it cuts out an arc of the circle of a certain length, okay? So, again, don't draw this. Okay, so here's a circle, and the circle, say, is a radius r from here to here, right? There's the radius of the circle. Suppose I make a central angle like this, like something like that. And notice this is a radius over here too. Right? How does the arc intercepted by that central angle compare to the radius? Now the radius is a line segment. That's easy to measure. These arcs aren't as easy. You can't just take out a ruler and measure it because it's a curve. But you can clearly look at this. How does this arc, the length of that arc, compare to r? It's clearly bigger. You can see that. But that length is clearly bigger than that length, okay? So I can draw a central angle whose arc it intercepts is bigger than r. Likewise, let me draw another circle of, radius r. So from here to r. Suppose I do a central angle that's small, like that. Okay? How does that arc, the length of that arc, compare to the radius? It's smaller. Okay? So that arc length is less than r. This arc length is bigger than r. Doesn't it make sense that somewhere between this angle and that angle, I could draw an angle where the length of the radius and the arc are the same? If I can draw one that's bigger and draw one that's smaller, there must be a way to draw an arc that has the same length. So that's what I want to attempt now. So try to draw that with me. I may not be perfect, but okay, so here's a circle, and here's the initial side. This is the radius of the circle, r, from here to here. So somewhere between that first angle I had and the second angle I had, there has to be an angle where the length of the arc is the same as r. Now, where does that look like? Maybe, well, maybe not. Maybe here. No, I don't have a very good circle. That's the problem. All right, that's not too bad, I suppose. All right, well, it's maybe a little bit bigger. So this length is r, this length is r, and I'm claiming that length is r. That's what I'm trying to draw. Hopefully you had more success than I did. Okay, so each of the radii here is r. The arc length is also r. So when you draw a picture like this angle that I've drawn here, the central angle right here, has a measure of 1 radian. Notice this is a radius, this is a radian. Radians is another measure for angles. So we have degrees, minutes, seconds, and radians. Notice here, we approach this in a different way. When we did degrees, we said all the way around was 360 degrees. And then so how big is one of them? Well, it's tiny, tiny. Notice what we did here. Here's a picture of 1 radian. It's just like the first graders. Here's a foot. So I'm doing the same thing for you. There's 1 radian. So look at that and get an idea in your head. There's an angle of 1 radian. Right? So which is bigger, 1 radian or 1 degree? Again, 1 degree is tiny, tiny. 1 radian is a lot bigger than 1 degree. All right? So there's a picture of 1 radian. So get that in your head that that's what 1 radian looks like. Okay? And notice it doesn't depend on the size of the circle. If I drew a big circle and did the same thing, the 1 radian will have the same measure. So it doesn't matter how big your circle is. The key is that the r's are the same. So if your radius is bigger, that will be bigger, and the angle there will still be the same. Okay? So there's a picture of 1 radian. Now with that in mind, just to get a feeling for what other measures would be, I say sketch angles in standard position of measures 1, 2, and 4 radians. They're not degrees, but radians. Because everything in calculus, and the whole point of this course is to get you ready for Calculus 1 next semester. 99.9% of the time, you're going to be using radians in calculus, not degrees. So some problems may give something in degrees, but the calculus is based on radian measures. So you need to get a good feeling for radians. You cannot convert every radian problems back to degrees just because you're resisting radians. That's not going to help you in the long run, okay? You need to get a good feeling for radians. Okay, so sketch angles look good. Okay, so standard position, remember, means initial side on the positive x-axis. There's my initial side. And now how big is 1 radian? We just drew a picture of 1 radian, so we have a feeling for how big that is. It was roughly that. So there's 1 radian. Right? Keep in mind also in terms of units, if you don't write a unit on the angle, that means radians. So be careful. If you mean 20 degrees and you write 20, that's wrong. This is 20 radians because you didn't put any units. If you mean degrees, you need to put a degree sign. If you mean radians, you can leave it off. You can always write, rad after for radians if you want, but you don't have to. Okay, there's a picture of 1 radian. The next one says, do it again for 2 radians, okay? Standard position, initial side on the positive x-axis. Now, based upon what we drew here, where would 2 radians be? It's not going to be in the 3rd quadrant. 2 of those is not going to be all the way down here. It's somewhere over here. So, roughly, I'm just guessing. Somewhere like that. There's 2 radians, approximately. The key is what quadrant is it in? It's clearly not in the 3rd quadrant. So there's a picture of 2. Now, where's 4 going to be? Well, 4 is double that. Okay. Now, is that going to be all the way over here? No, that's not big enough, okay? So where is that going to be? It's somewhere down here. So there's a picture of 4. Again, I'm just kind of doing rough. And that may be too far, but it's in the 3rd quadrant, that's the key. Right? So you imagine 4 of those is going to be over here somewhere. That's all I want you to get out of this problem. Clearly 2 is going to be here, 4 is going to be there. Okay, now, so we have an idea of how big a radian is, and we know how to convert from degrees to minutes and minutes to seconds, and you can go seconds to minutes through minutes, so seconds to minutes to degrees. Okay, so what about converting degrees to radians and vice versa? Right, so I'm explaining the next paragraph in the note, so I'm going to say it orally, but it's written there for you. So let me draw the picture again of my 1 radian, roughly. Okay, that's roughly 1 radian. And notice if my radius is r, how big was the arc length? It was r. That's how we got the 1 radian. If the radius and the arc length are the same, that's an angle of 1 radian. Okay? Now what if I added a radian next to that? Okay, what if I drew the picture again and I added another radian here? This may not be to perfect scale. Right? So if I put another radian here, notice that's an arc length of r as well. So 1 radian intercepts an arc of length r. 2 radians intercepts an arc length of 2r, doesn't it? What if I added another one? Another one. Well, there's another 1, there's an r, and there's an r. So 3 radians would intercept an arc of 3r, wouldn't it? Now what about a half a radian? Suppose I cut this in half. Half a radian would intercept an arc length of how much? Half r, because that was r and I just cut it in half. So 1 radian intercepts an arc of length 1r. 2 radians intercepts an arc of length 2r. 3 radians intercepts an arc of length 3r. Half a radian intercepts an arc of length half r. Do you see the pattern? Okay. So 2 pi radians would intercept an arc of length what? Okay. So 1 radian intercepted 1r, 2 radians intercepted 2r, 3 radians intercepted 3r, half a radian intercepted half r, 2 pi radians would intercept an arc of length 2 pi r, right? Remember, don't let the pi throw you. 2 pi is a number just like 1 is. Okay, it's just a real number. Right? Half a radian intercept half r, 2 pi radians will intercept an arc of length 2 pi r. But what is 2 pi r in terms of an arc length? Remember from your geometry, 2 pi r, where r is the radius of a circle, was the circumference of the circle. 2 pi r is all the way around. Right? It's the perimeter of a circle. Right? The circumference of a circle is 2 pi r. Well, wait a minute. If 2 pi radians cuts out an arc length of 2 pi r, and 2 pi r is all the way around, what does that tell you about 2 pi radians? That's the angle that goes all the way around. So what do we learn from this? 2 pi radians is the same as 360 degrees, right? Because 2 pi was all the way around. Now notice if I divide both sides by 2, you get pi radians is 180 degrees. And that's our conversion, right? Like, 3 feet makes a yard, 60 minutes is a degree, 60 seconds is a minute. Pi radians is 180 degrees. That's your conversion factor you need to memorize. Okay? Okay, so if you didn't quite understand the argument, that's okay, as long as you understand pi radians is 180 degrees. Okay, so the next example is trying to get you to get a good feeling for radians without converting to degrees. So there's 4 pictures I want to draw here. It says construct angles with radian measures of 10 pi, 3 pi, minus 2 pi over 3, and 5 pi over 3 without converting to degrees first, okay? We don't want to convert to degrees. I want you to get a good feeling for what degrees are radians are like. Okay, so we're going to do these in standard position. So we have our x, y axes, no problem. And again, we're going to try to be close, but it may not be perfect, right? We're sort of approximating. Okay, now what's the way to think about 10 pi? Again, I'm not converting to degrees. 2 pi radians was once all the way around. So how do you think about 10 pi radians? Well, that's 5 2 pi's, isn't it? 5 times 2 pi is 10 pi. And 2 pi was all the way around. So 10 pi is 5 times around. Right? So you don't have to convert to degrees. So there's my initial side. 10 pi is 5 times around. So, and it's a positive angle, so I'm going counterclockwise. 1, 2, 3, 4, 5. And it stops there. So this is a quadrantal angle, right? The terminal side is on one of the axes. And there's a picture of 10 pi radians. So I didn't have to convert to degrees. Right? It was 5 times around. Okay, let's do the next one, 3 pi. So the initial side, the standard position, positive x-axis. Now what's the way to think about 3 pi? Now 2 pi doesn't divide 3 pi evenly, but how can you think of 3 pi? Think of 3 pi as 2 pi plus pi. 2 pi plus 1 pi is 3 pi. Whenever an angle goes around more than once, now this was easy, it was 5 times around, I didn't have to do anything. Whenever I have an angle that goes around more than once, I pull off the complete rotations first. So like that's why I pulled off 2 pi here, right? So if this had been 5 pi, I would have said 4 pi plus pi, because 4 pi would be twice around. So this is once around 2 pi. Okay, there's one complete revolution. Now how much more is pi radians? Well, if 2 pi is all the way around, pi is halfway. So I have another halfway around to go. And there's the terminal side. So this is another quadrantal angle. So this is 1.5 times around, right? 3 pi is 1 time around plus a half. But I didn't have to convert to degrees to do this problem. Okay, now what about the next one? Minus 2 pi over 3. Okay, now here's how you want to think about this one. Think of this as minus 2/3 pi. So don't think of the 2 pi over 3. Think of it as the fraction, minus 2/3 pi. Now the negative, all that means is we're going to go clockwise, right? So in standard position, a negative angle goes down. Now here's the way to think of this one without converting to degrees. So negative pi is halfway around, but we're going 2/3 of the way. Well, where's 2/3 of from here to here going to be? It's going to be down here in the third quadrant. Again, most of the time in this course, we're only interested in which quadrant we're in, so I'm not going to be trying to be super precise, but right? Just imagine chopping this from here to here minus pi radians into 3 pieces, right? 1, 2, 3, and eat up 2 of those. So that's going to put me roughly, I don't know. So there's minus 2 pi over 3 radians. Again, think of the pi. Pi is halfway around, so this says do 2/3 of halfway. So if you chop this up into 3 pieces, 2 of the pieces would take you to here. So there's a picture of that. Now what about 5 pi over 3? I want to do the same thing. Let me think of this as 5/3 pi. Okay. Now again, I'm going to think of the 5/3 as a mixed number, 1 and 2/3. Right? So 1 and 2/3 pi. Well, where's that going to be? Well, there's a positive angle, so we're going to go in the counterclockwise. So 1 pi takes me to here. I'm not finished, right? That's only part way. And notice this was 1 and 2/3 pi. I just used up 1 pi. Now I have to use up another 2/3 pi. So I have to continue on. Again, 2/3 pi. Pi would be, halfway around. Chop that up into 3 pieces, and I need to use up 2 of them, just like I did here. So but I'm going this way instead of that way this time. So if you chop this up into 3 pieces and use up 2 of them, that's going to put you roughly. Yeah. So again, I don't have to convert to degrees to do that problem. Right? So let me do this one more time. So think of 5 pi over 3 is 5/3 pi. Think of 5/3 as 1 and 2/3 pi. So 1 pi takes me to here. That part's done. I still have 2/3 pi to go. Well, 1 pi would be the other halfway around, but we're not going 1 pi, we're doing 2/3 of that, 2/3 pi. So chop that up into 3 pieces, so 1, 2, 3, and use 2 of them. So there's a picture of that angle. Again, you need to start thinking in terms of radians. Sometimes you do want to convert to degrees for various reasons. We'll wind up doing that later, actually, in chapter 5, and so, on certain problems. It's just not worth the effort to do it in radians. It makes it too hard. But you need to get used to thinking in radians because everything in calculus is done in radians. Okay, that's the first half of this section.